Okay, in this video we're going to talk about the Poisson distribution. So there's a few things that you have to be aware of and that have to be true in order to be able to use this distribution. For a discrete random variable may be modeled by a Poisson distribution provided that events must occur at random and independently of each other in a given interval of time. And that's kind of what's going to signal to you when you're reading a problem on the test that it is a Poisson distribution, because you're going to be given an interval of time or space. And you're also going to be given the average number of events in that interval. And a lot of times we use lambda, that's the Greek letter lambda, for that. The average number of events in the interval have to be uniform and finite. Okay, so obviously can't be infinity, and it has to be consistent. So the average for per day or per mile or something like that. So we're going to let x represent the number of occurrences in the given interval. And then this is our formula here. So this is on your reference sheet, and this is very easy to do, but know that R is really the number of what you're trying to find. So we could look at it kind of like the number of successes. If we're trying to find 2 or more cars, then R would be 2. Okay, and you have R here, and you have R down here with the factorial, and then you have lambda. Let me erase that. You have lambda and lambda here. So this is your formula, and I'm going to show you how to use it. It's very easy. And R has to be numbers like 0, 1, 2, 3, and 4. We can have 2 cars or 3 cars or 0 cars, but we're not going to have negative numbers and we're not going to have decimals. Okay. And lambda, remember, is equal to the mean number of events in the given interval. You have to pay attention to that given interval because sometimes it changes. Okay, so our notation would be, we have x, and then we have this little squiggly here, and then we're going to say PO for Poisson. It's a Poisson distribution, and inside our parentheses we put lambda, which is our mean number of events in the given interval. So we put lambda there, okay? So, for example, if I wanted to do the probability that x equals 0, using just this right now, I'm not going to use a number for lambda, I would have e to the negative lambda, and you can't forget that negative sign there because it has to be there or your answer will be wrong. And then this would be times lambda to the 0 power over 0 factorial. Now, this is just going to become 1. So ultimately, when you're doing the probability that x equals 0, you're just going to get e to the negative lambda. But if we wanted to do the probability that x equals 1, we would do e to the negative lambda, and then we would have lambda to the first power over 1 factorial. Now, anything to the first power is itself, and 1 factorial is just 1, so this actually becomes e to the negative lambda times lambda. Let's do one more. The probability that x equals 2 would be e to the negative lambda, whatever that is, and then we would have lambda squared over 2 factorial. So this would be e to the negative lambda. Now I'm going to have lambda squared. I can, 2 factorial happens to be just 2. So I could write like 1/2 lambda squared, or I could leave it like this. It doesn't matter. But that's all you're doing. Negative lambda, and then whatever this number is, this 0 here, is going to match this exponent and this number here in front of your factorial. So we had 1 as an exponent and 1 in front of your factorial. Otherwise it's lambda, and then we start with e there. So let's look at an example. The number of defects in a wire cable can be modeled by a Poisson distribution with a uniform rate of 1.5 defects per kilometer. Find the probability, and we have 2 options here. So let's first write, we're going to have a Poisson distribution with our 1.5 as lambda, and I like to make a note that this is per kilometer, because in parts of questions, part 3 or part 4, if we had that, this could change. And if our given interval changes, then we have to change our lambda based on that, and you'll see that in a future example. So for part 1, we need to find the probability that a single kilometer of wire will have exactly 3 defects. So we are trying to find the probability that x equals 3. Well, that's just going to be e to the negative lambda, and remember this is lambda, so 1.5. We're going to have lambda, and then whatever this number is, we're going to have that as our exponent, and then 3 factorial on the bottom. And then that can just all really be done in your calculator. When you do that, you get 0.126. So that's the probability of exactly 3 defects. Now, for part 2, it says we're supposed to find the probability that a single kilometer of wire will have at least 5 defects. So this would be the probability that X is at least 5 would mean greater than or equal to 5. And this is different from our binomial distribution because I don't have a number of trials. So if we were going to do this, we would have to do 5, 6, 7, 8, and we have no stopping point. So you have to use the alternative for this. You have to say, well, if X is greater than or equal to 5, the alternative to that is to do 1 minus the probability that X is less than or equal to 4. And that's what I'm going to find. So to set this up, remember I need to use brackets here. And then I have to do 0, 1, 2, 3, and 4. So we're going to have e to the negative 1.5 times 1.5 to the 0 over 0 factorial. Now this is all 1, so technically you don't have to write that. I just want you to see it on your notes. Then I'm going to have e to the negative 1.5 times 1.5 to the first over 1 factorial. E to the negative 1.5 times 1.5 to the second over 2 factorial. We're going to do this until we get to 4. So 1.5 cubed over 3 factorial. And then 1.5 to the fourth over 4 factorial. And then you would need to be really careful with your calculator in typing this in. Now, a couple things you could do. You could store 1.5 as x and then put x's where all your 1.5s are. That would be easy. You could actually take out an e to the negative 1.5 and then do all of this part first, because we could take it out as a greatest common factor and then multiply that. But however you do that, you need to be able to find the answer to this. And when you do all of this math very, very carefully, you get 0.0186. That's the probability of at least 5 defects. Okay, so I talked about possibly having to adjust based on your time intervals. So when adjusting time intervals when needed, they're going to give you a lambda based on a specific time interval, and you're going to have to adjust it if that time interval changes. So Jasmine is considering buying a telephone answering machine. He has one for 5 days free trial and finds that 22 messages are left on it. So in 5 days, 22 messages were left. Assuming that this is typical of the use it will get if he buys it, fine. Now, part 1 actually asks us to find the mean number of messages per day. If that wasn't there, you'd have to do that anyway. Okay, but if there were 22 messages left over 5 days, then we can say that's 4.4. So the mean number of messages per day is 4.4. And of course, you can leave it as 4.4, or you can use the fraction 22 over 5. It doesn't matter. So then for part 2, we are asked to find the probability that on one particular day, so this part that we're trying to find the probability on has to match this interval that we have. So on one particular day, we're trying to find the probability that there will be exactly 6 messages. So that is the probability that x equals 6. Now I should probably, let's state our distribution. It's Poisson with 4.4 as our lambda. Okay, so the probability that x equals 6 is going to be e to the negative 4.4 times 4.4 to the 6th over 6 factorial. And then you're just going to do that in your calculator. And when you do that in your calculator, you get 0.124 to 3 significant figures. Okay, but if you look at part 3, it says to find the probability that there will be exactly 6 messages in 2 days. Up here we had 4.4 per day, so that's in 1 day. So how do we get it for 2 days? We need to multiply 4.4 by 2, which is going to give us 8.8 per 2 days, or every 2 days, okay? So this is what I'm going to be using if I'm trying to find the probability that there will be 6 messages in 2 days. So the probability that x equals 6 is going to now be e to the negative 8.8 times 8.8 to the 6th over 6 factorial. Okay, and when you do that, you get 0.0972 to 3 significant figures. Okay, so the biggest thing here is you have to pay attention to your interval. You have to be very careful with that part. Okay, all right, last little part here. The sum of 2 or more Poisson distributions. So if x and y are 2 independent Poisson random variables, which means lambda and mu, this is mu, the Greek letter, respectively, then we can use t as total. You can really use whichever variable you want, would equal x plus y. And so t would then also be a Poisson random variable with mean lambda plus mu. So for example, if I have a Poisson distribution as x with lambda as the mean, and I have a Poisson distribution, let's call it y, with mu as the mean, as long as those are within the same interval, and if not, I have to adjust those, and I want to put them together, so a total, x plus y, then all I have to do is add their means. Okay? So here's an example. A rare disease causes the death, on average, of 2 people per year in Sweden. So I'm going to call this one S. And I'm going to say that's a Poisson, and 2 is my mean. 0.8 in Norway, so I'm going to say N is Poisson with a mean of 0.8. And then 0.5 in Finland. So F is Poisson with 0.5. Okay? As far as we know, the disease strikes at random and cases are independent of one another. What is the probability of 4 or more deaths from the disease in these 3 countries in any year? So they're asking us to put them together. They don't care about the separate countries. So we're going to say T is really equal to S plus N plus F. Okay, so I'm going to have T as a Poisson distribution, and I'm just going to add 2 plus 0.8 plus 0.5, and that gives me 3.3. Okay, so what we want to find is the probability that there are 4 or more deaths. So the probability that x is greater than or equal to 4. And remember, we're going to do 1 minus the probability that x is less than or equal to 3. And again, that setup is we have to do 0, 1, 2, and 3. So we're going to have e to the negative 3.3 times 3.3 to the 0 over 0 factorial plus e to the negative 3.3 times 3.3 squared over, times 3.3 to the first, we can't skip that one, over 1 factorial plus e to the negative 3.3 times 3.3 squared over 2 factorial. I know you get the idea. So this one is going to be 3.3 cubed over 3 factorial. And you're going to do all of that very carefully and then subtract your answer from 1. Okay? When we do all of that, we get 0.420 to 3 significant figures. So that's the probability that there are 4 or more deaths from those 3 countries in any year. Okay? So actually there's one more example here, and I want you to take a minute and I want you to try this example and then check your answer with me. Okay, so on a lonely Highland road in Scotland, cars are observed passing at a rate of 6 per day, and lorries at the rate of 3 per day. So I'm going to go ahead and write C as Poisson, and there were 6 per day, and lorries is also Poisson with 3 per day, and I'm going to just make a note that that's per day. On the road is an old cattle grid that will soon need repair. The local works department decides that if the probability of 2 or more vehicles per hour passing is less than 1%, then the repairs to the cattle grid can wait until next spring. Otherwise, it will have to be repaired before winter. When will the grid have to be repaired? So now notice we're asked about per hour here, and this is per day. So you can do this kind of in either order, but I'm going to go ahead and change this to hours. So if this is 6 per day and there are 24 hours in a day, then I'm going to do 6 divided by 24, and I'm going to get 0.25. And then for this one, I'm going to do 3 divided by 24, and I'm going to get 0.125, and that's going to be per hour. So now if I put these two together, this is going to be C plus L. So I'm going to say that T is a Poisson distribution, and when I add 0.125 and 0.25, I get 0.375, and this is per hour. So now I want to find the probability of more than 2 vehicles. So I'm trying to find the probability, and I really should use T here because it matches that. So try to get in the habit of doing that. I know we're used to using X, but you should match the variable. So I'm trying to find the probability that T is greater than 2, more than 2. And I need to do the alternative. So the alternative to this is actually 1 minus the probability that T is less than or equal to 2. So the 2 wasn't included here, so it has to be included here. So I'm going to have 1 minus, I'm going to have brackets, I'm going to have e to the negative 0.375, and this is going to be 0.375 to the 0 over 0 factorial I know you know this part's easy, so just make sure that you wrote it correctly. And I'm going to have e to the negative 0.375 times 0.375 squared over 2 factorial. And you're going to do all that math very carefully, and then you're going to remember to subtract it from 1. And when you do that, you get 0.00665. So now, we were trying to find out if the probability of more than 2 vehicles is less than 1%. So if I made this a percent, it would be like 0.6%. So this is definitely less than 1%. And so in that case, they can wait until next spring. So when will the grid have to be repaired? The grid will be repaired next spring. Okay? And that's all there is to it. So review what you need to, and I'll see you in class.